In this video, we're going to talk about local linearity and tangent lines. So the local linearity property is the idea that when you get really close to the graph of a function, you can zoom in a long ways, the graph starts looking like a straight line. Instead of a curve or some wiggly line, it looks straight. And if a function has that local linearity property so that it looks straight when you get really close, then the line that it looks like is going to be called the tangent line. That's going to be an important thing in calculus. So let's look at an example. Oops. This is 2 times the natural log of x, and here is a typical graph of that function, and you can see this is not a straight line, it has a nice curve to it. What happens if we choose a particular point and zoom in closer? So I'm going to choose the point 1, 0, just arbitrarily chosen, nothing special about that point, just choose something. And I'm going to zoom in there. So notice I've adjusted the x min and x max here on my plot so that I've gotten closer to that point 1, 0. So here's the point I'm zooming in on, and you might still see a little bit of a bend here, but this is definitely looking straighter. If I zoom in some more, okay, notice how close I am now to 1, 0 with that x min and x max. And now, just looking at this, it looks like it's a straight line. Now I know in the back of my head that this is not a straight line. I saw that it's a nice curve on my first graph, but it looks straight when I get really close to this point. So locally, it's linear. That's the idea of local linearity. All right, here's a second example. I want to think about the function cosine of x near 0, 1. And in this one, I have made a little animation video, and I'm going to zoom in on this point right here, 0, 1, right at the top of this. You'll notice that the x and y axis will change as I zoom in. I want to keep the scales the same so that this picture doesn't get distorted. And the closer I get, I'm zooming in. Notice how I'm just getting closer, closer, closer. The farther I zoom in, the straighter this becomes, till eventually this looks like a horizontal line there. So it looks like cosine of x also has the local linearity property, at least at that point 0, 1. Just because it has local linearity property at one point doesn't necessarily mean it does at a different point. So kind of each point, it depends. For example, let's look at absolute value of x at the particular point 0, 0. And again, I adjusted the y min and y max to maintain the scales here. Otherwise, Sage might kind of adjust them and hide what I want to show. So what I see right here at 0, 0 is not a straight line. I see this corner. Now notice that I'm already zoomed in. I'm not going to zoom in repeatedly on this thing because the picture will look the same. No matter how far I zoom in, I'll never see a straight line. I'll see this, well, 2 straight lines that kind of meet together at this point. So I'll see a sharp corner there. Doesn't matter how close I get. As long as I am zooming in at 0, 0, I'm going to see this corner. This function does not have the local linearity property right here at 0, 0. Now it does have it at other points. In fact, at other points, anywhere else, it is a line. So if I zoom in, say over here at 0.01, this thing is already a line. This is a line y equals x on this side of absolute value. Anything over here, this is the line y equals negative x on this side. It's already a straight line. It's only right here at this corner where those 2 lines meet, where it does not have the local linearity property. Now, what we've seen above, we don't want to just look at a graph alone. I had to adjust the y min and y max to keep the scale the same. You know, if I let Sage choose that for me, the picture can get distorted, and it kind of obscures the fact that it's looking like a line. So I don't want to depend on the graph. So I want a more algebraic way of doing that, and that leads us to this idea of tangent lines. So if some function f has the local linearity property at a particular point, so I'm going to call that particular point x0, and then x0 will be the x value, and then of course the y value is the function value there. So f of x0 is the y value that goes with x0. If the function has a local linearity property, the graph of f looks like a line, and the line that it looks like is going to be called the tangent line at that point. The particular point we're looking at is going to be called the point of tangency. Now this tangent line depends on which of this initial starting point we choose. So if I choose one particular point of tangency and you choose a different point of tangency, we're probably not going to get the same tangent line. So tangent line depends on two things, the function itself and then the particular point that we're looking at on that function. In order to find the equation of a line in general, we need two pieces of information, either 2 points on the line, or if you know only 1 point on the line and the slope of the line, that's also enough. Now we know 1 point on this tangent line. It's this point of tangency, this given point. We want the tangent line to touch that point, of course. We don't know a second point on this line. The other points we know are points on this function. Unless this function is already straight, a second point on the line isn't going to give us, our second point on the function isn't going to give us the right line. But there is a way we can track down the slope of this tangent line, and that's what we're going to do. The way we're going to get this slope is by approximating it with a second point on the curve, and then improving that approximation till something happens. And you'll see what I mean by that in a minute. Okay, so we start with this point of tangency that's given to us, and we're going to choose a second point close by. And I'm going to call it this. H is how far away the x value of the second point is from the starting x value, the x sub 0, the x value for the point of tangency. So I moved a little bit away, h units away from my starting point in the x direction. And I want to see what happens there. So here's the sample graph. So this in blue is just some random function f, and here's a particular point on that function that I care about, and here's a point close by. I've moved h units away in the horizontal direction, so the distance from this point to this point horizontally is h units, and this is the second point now on the graph, and I just connect those two dots with a straight line. That's called a secant line. Now that's not the tangent line. If I were to zoom in on this function right here, this green line here is not the line it would look like. That's not the tangent line, but at least it's an approximation. The idea is to make the approximation better by making h smaller. That is, move this point here closer, closer, closer to the first one. Now you can't move it all the way to the first one, otherwise you wouldn't have 2 points and you can't make a line, but we want to get closer, 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 and closer and hope that that goes somewhere. It doesn't just, I don't know, wander around, but actually ends up some sort of answer. Okay, so make h closer and closer to 0, which moves our second point closer to the point of tangency. Now, that sounds like a limit. That's why we went through the whole limit concept before. So the slope of the secant line through those 2 points, so the point of tangency and this point h units away, the slope of the line between those, just rise over run, so difference in the y coordinates divided by difference in the x coordinates, and of course this x of 0 cancels out, and so you get the difference in the function values divided by h. We want to see what happens to that slope. This is the slope of that green secant line in my picture. We want to see what happens to that slope as h gets closer and closer to 0. Or in other words, we want to take the limit as h approaches 0 of this quantity. This is the difference quotient that you learned about in pre-calculus. So your pre-calculus teacher made you do that without the limit part, of course, but this part, they made you do various algebraic computations probably with that thing, and they didn't really tell you why. Well, here it is. We want to now take the limit of this as h approaches 0, and what does that give us? If the function f has a local linearity property at this particular point, then that limit will exist, and vice versa. If this limit exists, the function has a local linearity property, and that limit will give us the slope of the tangent line. So if I zoom in on the function, it looks straight. I want to know what is the slope of that line that it looks like. Then the slope of that line it looks like is equal to this limit. Alright, so once you have a point on the line, the point of tangency, and you have the slope of the line, which is given by this limit, that's enough to find an equation for the line using point-slope form. So here's the point-slope form for an equation of a line. It's the difference in the, or y minus a given y value is equal to m, the slope, times x minus the given x value. So x0, y0 is a particular point on the line, and m is the slope. You learned about this in general back in pre-calculus and before. In this particular case, the particular point we have on the line, x0, y0, is x0 is the x-coordinate, y0 is the function value, which is f of x sub 0. The slope is given by that limit of the difference quotient as h goes to 0. So here's an equation for the tangent line, just replacing f of x sub 0 for y sub 0, and then m, I didn't write it here, but this limit would go right here in the place of m. And for various reasons, it would be convenient to add this f of x sub 0 to both sides and get this equation for a tangent line at the particular point x equals x sub 0, y equals function value plus slope times x minus the x value, where the slope m is given by that limit. This is our general formula for a tangent line. This tangent line exists as long as the limit exists. If the limit exists, the function has the local linearity property, and vice versa. Okay, let's look at an example and see how secant lines approach the tangent line graphically. So I have an animation. We're going to look at secant lines for this curve, 2 times natural log of x. The particular point is the one we looked at earlier. Okay, we zoomed in on this graph at 1, 0, and we saw that the graph of 2 times the natural log of x looks straight near that particular point. So I'm going to graph a secant line that connects 1, 0 with a second point close by. My h is going to start at 1, so it'll be 2, whatever the function value there, I guess 2 times natural log of 2. And then the h is going to get closer and closer to 0, and we want to see what happens. Okay? So in blue, we have 2 times the natural log of x. Here's my point of tangency, 1, 0. This is where I want the tangent line. Here's the second point, the x sub 0 plus h, and the function value there. This point's going to move closer and closer and closer and closer. Okay? So we'll start this animation and hope it decides to run. Nope, didn't decide to run. Try again. Okay, there it goes. Notice that this green line is getting steeper and steeper and steeper, but it's not just getting steeper like off to infinity. There's some sort of boundary or limit, and that's this red line. The green line never goes past that red one. Okay, the slopes are getting steeper and steeper and steeper, but there's a boundary to how steep it can go. And that's it right there. Though that red line there is the tangent line, which I got using that formula up above that I gave you. And the green secant lines get closer and closer and closer to this red tangent line as h approaches 0. In this case from above, so all of my h's were above. Same thing happens on the other side. So do the same thing, same function. Now I'm going to make my h negative, so my second point's here. It's actually kind of hidden behind there. But h is going to get closer to 0, and the second point's going to move closer and closer to this point of tangency. And what happens here is the green line, you start getting less and less steep, but there's some sort of limit or boundary. These green secant lines are approaching this red tangent line. So from the left or from the right, we see the same picture. When you make a secant line and you make your second point closer and closer to your point of tangency, there's this limiting line, the tangent line, that it approaches. Alright, let's look at cosine x again at the point 0, 1. And again, I'm going to look at some second points close by. I'm going to move my second point closer to the point of tangency, which is right here. And as I get there, this line starts looking more and more and more horizontal. And that's the limit here. The limit is 0. So these secant lines start looking like they're closer and closer and closer to a horizontal line with slope 0. And when I take the limit, that's exactly what happens. Same thing if I start on the other side. So here h is negative, so my second point is on the other side of my point of tangency. Here's my point of tangency. I want the tangent line there. I make secant lines where the second point's closer and closer and closer to 0, 1, and the line starts to flatten out. It gets closer and closer and closer to the horizontal line. Alright, here's another example, and this was similar to what you're going to do on your assignment for this section. I'm going to give you a function. I'm going to give you a particular point on that function. I'm going to ask you to find an equation for the tangent line. So first off, I need the slope. So here's the formula for slope. All I did was take the formula from up above and I replaced x sub 0 with 1. 1 is the particular x value given the question. So each of these is 1. That's the particular x value. I'll let Sage do this limit for me. So I defined the function. I typed in this difference quotient. I took the limit. Remember how to use the limit. Type the word limit, parentheses, the thing you're trying to take the limit of, which is that difference quotient thing. Notice this parentheses here around the top of the fraction. Those are not optional. Okay, you have a difference, a subtraction on top of a fraction. Order of operations requires these parentheses to force that subtraction to happen before the division. So don't forget those parentheses around the top of this fraction. Comma, and then you tell it what h approaches. H equals 0 here is the stand-in in Sage for h approaching 0. Okay, and when you do that, Sage says 2. So that means the slope of the tangent line is 2. Here's my equation for the tangent line I gave you above. Function value plus the slope, x minus the x value. I'll type it in just like that. The tangent line, which I'll call TL just for tangent line. Function value at 1, so this is f of 1, plus the slope, 2, which is from up here, just copy and paste. And then times, don't forget this multiplication, that needs to be there. Sage requires you to type every multiplication. And then x minus the particular x value, which is 1. Okay, notice where that number 1 shows up here. Okay, number 1 is the particular x value given in the question. It shows up twice in the slope formula, in this limit. It shows up twice in the tangent line formula, once in the function and once just alone. Okay, so here's the tangent line. I'm going to go ahead and graph the function along with its tangent line. So in blue is the function f, in red is the tangent line I just computed, and I put this point command here. It just puts this black dot so that I can see the point of tangency. If I were to zoom in on this graph right here, this black dot, I would see the red and the blue would start looking identical. Now out here they don't, but if you just look close to 1, right through here, you can just, even on this window, you can see the red and the blue are right on top of each other, close to this point. And the closer I get to this point, the closer these red and blue will be. One last example. What happens when you don't have the local linearity property? Something should go wrong in this whole process. So let's go back to the absolute value function at the particular point 0, 0. Remember, we saw up above that there's a sharp corner there. I said it does not have the local linearity property. So what happens? Let's try to compute the slope. So I define the function g. Here's the difference quotient now with g. I replaced the x sub 0 with 0, which is the given x value right up here. And Sage says und, which is a way of saying that that limit does not exist. The reason for that is because the one-sided limits are not the same. They both exist, but they're not the same. So as h approaches 0 from above, this limit is the absolute value of h over h when you simplify. And if h is approaching 0 from above, that means h is positive, and so the absolute value of h is h. And so h over h is 1. This is a limit as h approaches 0 from above of 1, and the answer is 1. When h approaches 0 from below, h is negative. Absolute value of a negative number is its opposite. All right, so here negative h or minus h is actually a positive number because h itself is negative, and this h divided by h cancels out. That's 1, so you have minus 1. So the limit from above is 1, the limit from below is minus 1. The two-sided limit doesn't exist because those left and right limits are different. Now that's only the case at 0, 0, where this function does not have the local linearity property. Anywhere else, it works just fine. So for example, at negative 5, 5, there's the limit for the slope, and when I compute that, I get negative 1. And so the tangent line is, here's the formula for tangent line, it's the function value, in this case g of negative 5, plus the slope. Slope is negative 1 from here, and then x minus the x value, x minus negative 5, which is x plus 5. Now this thing actually simplifies into y equals negative x, which is not surprising. That is, the absolute value function equals y equals negative x. This is the same graph when x is negative. So here it is, absolute value, and y equals negative x is what this function is. So the tangent line is right on top of this function. The function's already a straight line, so it's its own best tangent line. Anywhere away from 0, 0. So I could, if I chose something over here, this is y equals x, this part, and y equals x would be a tangent line for anything on this side, and then y equals negative x is the tangent line for anything on this side, and right here in the middle at 0, 0, there is no tangent line.